Hello all, and welcome to your next week of Math Theory. We're going to be looking at 14.2 over the next week, which is about proving with countable sets. So get yourself ready for notes and we're going to get started. Now, with an objective like prove with countable sets, I'm hoping that the first thing most of you are asking is, what does countable mean? So defining countable over here, meaning that it has a cardinality, so it has the number of elements, equal to some subset of the natural numbers. So remember, the natural numbers are sometimes called counting numbers, and a countable set can be written out in an order. So you have the first element, the second, the third, whoop, that's not a 3, and so on. So this is what it means to be countable. Now, what we call the natural numbers, since a subset can also be itself, this is countable and it's called countably infinite. So you can have something that's countable. All finite sets are countable, right? You just count them all out. It might be a million elements, but you could do it. If it's infinite, you can say it's countably infinite if it's the same size as the natural numbers. So we can also say that it has cardinality equal to, and that is a weird symbol, and that's called aleph. It's called aleph naught with the subscript 0 right here. If we typed it out, it'd be a little bit neater. You can see it in your book. But this is aleph naught, and it is the smallest of the infinities, and it is the one that is countable. Sets that are, so as I said, all finite sets are countable. One thing to note is that we say if a set is infinite and its cardinality is not equal to the natural numbers, we call that uncountable. So, a lot of the things you're going to be doing is proving that things are or are not countable. So here we see in number 1, prove that the even numbers, so 2n, where n are in the integers, is countably infinite. So there's a couple ways to do this. One is what I think of as our goal, in this case, is to write a bijection f from the natural numbers to the even numbers. So not the natural. So what you've got here is that we want to show it's countably infinite, so we can say that. Now, sometimes in order to make ourselves easier, one thing that's really helpful is I'm going to say recall that we already know this is true. So we could also write a bijection to the integers, and because these are from the integers, since this is a subset of the integers, I'm going to do that instead. So I can, using the transitive property, write a bijection from the integers to the even numbers, and that will prove it just as well. And this is a lot easier in this case because I can say that f from the integers to the evens is just defined as f of x is equal to 2 of x. Not 2 of x, but 2x. Now, to show that it is injective, remember we just say f of x is equal to f of y, and we want to prove that both are true. So 2x is equal to 2y, x is equal to y. Excellent. We know it's injective. We then need to show it's surjective, which means that we want to say that y is some element of the even numbers. Therefore, by definition, y is equal to 2x for some x in the integers by the definition of even numbers. Therefore, we'll just use that x. So we'll say f of x is equal to y. So it is also surjective. So what that tells us is that E has the same cardinality as the integers, which we already have proven has the same cardinality as the natural numbers. By the transitive property, E has the same cardinality as the natural numbers, so E is countably infinite. So always remember you can use our old proofs to help yourself out. So in number 2, prove that if A and B are both countable, then A union B is countable. And this is going to be another one that's going to be really helpful in some of your homework problems. So since they're countable, I'm going to say that A is A1, A2, A3, A4, and so on, since we know we can list this out since they are countable. And I will use similar reasoning with B, B1, B2, B3, B4, and so on. Now I want to write out A union B in a way that I can count them. I want to be able to list them. So I'm going to use a similar logic that we used for when we were doing the positives and negatives for the integers. So I'm going to say A1, then B1, since we want to include in our intersection every element from both of these sets. Next would be A2, B2, A3, B3, and I think from here on we've established our pattern. And here's the nice definition of countable. Since the elements of A intersect B can be written as a list, then A intersect B is countable. It might be countably infinite, we don't know, but it's definitely countable. And for a lot of these, if you can make a list, that is adequate enough proof, at least in this class. All right, number 3. This one's going to be a little bit tricky, and you will definitely want to use this one for your homework. Prove that if A and B are countable, then A times B is countable. So we're going to start the same way as we did before with these sets right here, and I can even just copy and paste because I'm very sneaky like that. So we'll start by listing out our A and B. Now, when I multiply two sets together, if you remember from back in the beginning, I would write it as a table. So I'm going to do the same thing here, just to give myself an idea of how I want to list these elements. So I've got my product, and I've got my A's, A1, A2, A3, A4, then B1, B2, so on, B3, B4, so on. And the products are always going to be ordered pairs. So A1, A1, B1, A2, B1, A3, B1, A4, B1. I'm going to copy and paste the rest of these from the finish notes. Please pause the video and fill them in on your own. So these are the finished ones that you have access to. Doing a quick copy. Again, if you want to pause the video, I encourage you to do so. Fast forward. And here are our points. Now, we want to find a pattern that allows us to list these in an order. Because if we just go all of these ones first, we'll never ever get around to these ones again. So we can't just list them in rows because this doesn't ever have a traditional stopping point. So we're actually going to use a method that's used to prove that the rational numbers are also countable. And that's where we're going to start here. This is, I think, hopefully a reasonable first point. That's our first one. So A, B starts with A1, B1. our next point, we're going to go to in our list, we're going to go here. So then A2, B1. And then instead of keeping going in a horizontal line, we're going to turn so that we don't forget any of our points. A2, B2. From there, go back and grab A1, B2. And we're going to continue this zigzag line. So it's like, okay, well, do here, make a turn. We're going to go past that and then up here. And you're just going to make this zigzag all the way across. And hopefully you would see is that if we kept following this pattern, we are going to list all these numbers in this product in order without ever skipping or running into an infinity problem. So we can then say, since the elements of A, B can be listed in an organized consecutive way, A times B is countable. And this again is going to be a really helpful idea. One other idea that comes from this is that as you keep multiplying and multiplying, you can then say that if A sub n is countable for all n in the natural numbers, then A1 times A2 times A3 times all the way out to AN is also countable. So you can keep multiplying all the way out. One other important result of this, as I said, is to show that the rational numbers are countable. So just like the integers, they are equal to, their cardinality is equal to the natural numbers. And we can show this by saying that the rational numbers are going to have a cardinality that's less than A times B, where the elements, where A in A equals, and let's see, and B in B can be written as a fraction like the rationals, and this set's going to be bigger because there's plenty of simplified versions of sets. And here, A and B, since it's rational numbers, can be thought of as the integers, which we've proven over are countable. So a lot of new ideas. You've got the week to work through them. Please let me know if you're stuck on any, if there's anything I can do to help.